Hey kids, hope you're doing well. Uh, yeah, we're still at it here, right? Um, Last week of April, we're getting there. Hang in there. Overall, you guys have really been doing a very good job. So keep this up. If you have questions, see me during office hours on gray days. If for some reason those don't work for you, remember AAC has office hour options every day of the week. And don't hesitate to email me with questions as well if you have any. I'll try to answer them through email. So today we're going to start section 11.6, power theorems. There's an opener here. You should probably pause this here and try to do this opener yourself. There's nothing new here. It's just a review. I'll do the problem here in just a moment, but you should probably give it a try yourself. Okay, so the first thing when I see this, I think about drawing in a perpendicular to that chord, and that's of course going to cut the chord in half. And I'm just labeling my information here. It says DC is 10. Yeah, I got that. CA is 8, and OB is 9. Now, remember, OB is a radius. So I have a couple of right triangles here already, but in each of those right triangles, I only know one of the sides. So I'm going to create another right triangle by drawing in a radius. We've done that many times. And now I can use Pythagorean theorem with 81 minus 25. Of course, that gives me 56. So this segment here would be square root of 56. Now I know that can be simplified. I don't have a need to do that right now because I'm just going to square it again anyway. Because now I'm going to use this long skinny triangle. And I know that square root of 56 squared plus 13 squared will give me AO squared. So I have 56 plus 169. And that gives me 225. So obviously AO would be the square root of that, which would be 15. Now if AO is 15, let's see if we can answer the questions. AO is 15. That means AB is 12 from triples. And AF, of course, is 24. We just have to add in this other radius. All right. So, power theorems. There's some good stuff in the book, so if you really want to dive into this in a big way, don't hesitate to go through the book, okay? And they give you some good information here, but we're going to prove these power theorems as well. Here, I'm going to give you a couple of chords, okay? And we'll call this A, and this B, and this little C, and this little D. Now, what the power theorem states is that, you see, each chord was cut into two parts. This one was cut into parts A and D. This one was cut into parts B and C. I'm going to tell you what the power theorem states. The power theorem states that part 1 of the first chord times part 2 equals part 1 times part 2 of the second chord. So really it's just part times part equals part times part. So in this particular problem, obviously AD would end up equaling BC. So that is the power theorem. Now, over here on the right, we're actually going to prove it. Okay, obviously I would solicit input from you guys if we were doing this in class. And what you want to, how are we going to figure this out? Remember, if we go back a couple units, we got so much information from similar triangles. And this is going to come back to similar triangles as well. Okay. First, let's create some triangles. Let's go ahead and draw this in there. We'll draw this in there. Obviously, we have vertical angles. Okay. How can we get these triangles to be similar? Well, check out angle A. Angle A, I'm hoping you recognize it as an inscribed angle that intersects arc BC. Angle D is also an inscribed angle. It also intercepts arc BC. Well, if you have two inscribed angles that intercept the same arc, they are, of course, congruent. So we have similar triangles now, and I'm going to write that down, triangle ABE, and that would be similar. I'm going to make sure I match this up correctly to DCE. So that allows me to set up a proportion. And I'm going to say AE is to DE as BE is to CE. Now when I cross multiply that, I get AE times CE equals DE times BE. And you'll recognize if you look at the diagram, whoops, sorry, I'm at this middle point is E. You see that we've just proved the power theorem, okay? Because AE times CE, those are the parts of one chord. DE and BE are the parts of the other chord. So part times part equals part times part. How do we prove it? Similar triangles. Similar triangles is just huge. And you see there's two more of these things, okay? The next one is called a tangent secant power theorem. So there's my tangent. There's my secant. So that's the tangent. Now, this secant has what I call the external part right here. And then this whole thing. And again, I'm going to give you the power theorem, and then we'll prove it. What the power theorem states is that the tangent part squared, so this part squared, equals the external part of the secant times the whole secant. So I need you to remember, it's not external times internal. That's an easy mistake to make for people who go too fast. It's tangent part squared equals external times the whole. And we will prove it. This one's a little bit harder. However, you still do it with similar triangles. Obviously, we got to make triangles. So I'm going to draw in this. And now we actually have how many triangles in that diagram? I'm hoping that all of you guys said 3, right? 2 little triangles in the whole thing. Okay, so check this out. We got some cool things going on here. And, you know, first of all, I'm going to relate, I'll call this A, B, C, D. Let's look at angle C. Angle C is reflexive. It's an angle in this big triangle. It's also an angle in this little triangle. But the other thing that we have, you know, I want you, maybe you stop this and try to figure out how to prove this yourself, okay? It is going to be with similar triangles. What I hope that you recognize is that, you know, we're going to prove this big triangle similar to this little one. Check this out. Angle BDC. Angle BDC is a tangent chord angle. It's on the edge of the circle. It's half the arc intercepts. Angle A is an inscribed angle. It intercepts the same arc BD that this tangent chord angle intercepts. And it's also half the arc intercept. So that means that angle A must be congruent to angle BDC. So we have similar triangles, ACD, similar to triangle DCB. Okay, make sure you match those up correctly. Now this gives me AC. AC is to DC, as CD is to, I'll call it BC instead of CB, but so when I cross multiply, I get AC times BC, and then look, I get CD twice. And there, we've proved it. Tangent part squared DC equals, here's the external, and there's the whole. So it's all similar triangles. Again, rewatch is necessary, of course. One more. Okay, and this is called the secant power theorem. And just like I did above, I'm going to call this the external of that one. And then, of course, we have the whole. This is the external of this one. And, of course, we have the whole. The power theorem is going to be exterior times the whole of one secant equals the exterior times the whole of the other secant. Okay? So the important thing to remember here in all these power theorems, there is no external times internal. There's external times a whole in a couple of them. Okay? You can guess that we're going to do this with similar triangles as well. Okay, so there it is, and I'll call that A. I'm going to draw in these segments to make triangles. We got a bunch of triangles here. This can be a little bit confusing. But what you'll see here is we can prove these big skinny triangles. So I'm going to prove that triangle ACD is similar to triangle AEB. Remember, you should be able to see that pretty quickly. Obviously, angle A is reflexive, so there's one angle. But you see angle C intercepts arc BD. It's an ascribed angle. Angle D also intercepts the same thing, so they have to be congruent. So we got angle pretty quickly. What does this give us? This gives us AC. And AC matches to AE over there. I'm going to take AD. That's going to match to AB. And when I cross multiply that, sorry, that's a C, a little bit sloppy. AC times AB, you see that's whole times external. I always say external times a whole. Equals AD times I accidentally have, sorry about that. That should be an E down there. There we go. So you got three power theorems. Chord, part times part equals part times part. You have tangent secant with the tangent part squared equals the external times the whole. And then you have secant, which is, of course, external times the whole equals external times the whole. Most of these problems back here are pretty straightforward. And you can certainly try to do some of these yourself here. Maybe pause this right now, do these top four, A, B, C, and D, but these won't take you long at all. And I'll talk through them here in just a second. All right. WA is 2, AX is 5, WY is 10, so obviously that means that's 8. Find ZX, well, I'm going to find AZ first, so I'm going to do part times part equals part times part. So obviously 16 equals 5 times ZA. So that means you get 16/5 for AZ. Now, that's just that piece right there. And obviously, we have to find this whole thing. That's 25/5. So 25/5 plus 16/5 gives you ZX to be 41/5. Not hard, but your answers aren't always going to be pretty. Got a fraction there, no big deal. On the right, we have circle D. We are given that AD is 4, so that's a radius. BC is 2, so obviously this is 4 as well. BE, I'll call that X, that's the tangent part. So tangent part squared equals external times the whole thing. So obviously we're going to do square root of 20, which becomes 2√5. So that was pretty painless. All right, we're moving on. Looks like we're dealing with secant here. We got 6. We got 3. KL is 5. And JK, we got to find, we'll call that X. So set this up. Again, make sure you don't go too quickly. 3 is not 3 times 6, it's 3 times 9 equals external times the whole thing. Now, if I distribute and set it equal to 0, I'm going to get x squared plus 5x minus 27 equals 0. Now, no matter how hard you try on that, it's not going to factor. You're going to have to use quadratic formula on that. I'm not going to show that, okay? You can do quad form yourself if you like. You should get x equals 3.27, rounded, of course, which is our JK. And last one from the top, we got 2√5. We got this external part. We're asked to find QP. So I'm going to do tangent part squared equals external part. And I'm going to, you know what I'm going to do is I'm going to call this whole thing X. I think that's probably smart. So if I do a little division, I get X equals 13.3. Now remember, that's the whole thing. We're asked for QP, so we have to subtract out 1.5. And you should get QP to be 11.83 then. All right. I don't know if these down here are anything more challenging. It's just kind of show you about the power theorems. Let's go ahead and mark this stuff. If you want to try them first, that wouldn't be a bad idea at all. RE is 1, GI is 6. Now remember, if that's a perpendicular, that cut that in half. Now, the first thing, again, you should try this yourself first. The first thing that a lot of students do here is they start drawing in radii, because so many times we've drawn in radii when we have these types of problems with circles. But, you know, we do have this new tool at our disposal called power theorem, so don't, you know, hesitate to use that. I don't want you to forget about drawing in radii. Don't get me wrong, because that's still going to be helpful. But what I can do here right now is I can do chord, right? Part times part equals part times part. So obviously you get DE equals 9. So the radius is 5. So again, you know, if you start drawing stuff in, you know, you can probably still do it, but you just make a lot more work for yourself, okay? So don't forget about drawing in, but we do have these additional tools at our disposal. Almost done here. MR is 3, RP is 6, NQ is 11. So, you know, I don't know I just know this whole length. I'm going to call this x, and this, of course, is 11 minus x. So this is chord chord again. And we will have a quadratic here. 18 equals what? 11x minus x squared. I want my x squared to be positive. This one actually does factor, 9 and 2. So you get x equals 9 or x equals 2. And remember, both of them are correct. So we have two possibilities for this length. We know that this core has been cut into lengths of 9 and 2, but we don't know which one's which. So you would have to list both possibilities there. And this last one, looks like we're going to have some, I'm guessing I'm going to use that tangent part first. So tangent part, let me call this y, seeing that there's already an x there. Tangent part squared equals the external part times, remember, it's the whole thing, which is y plus 10. 64 equals 5y plus 50. So 14 equals 5y, so we get 14/5 equals y. Now we can finish up with chord chord. 12x equals 5 times 14/5, and that was convenient. The 5's cancel. So x equals 14/12 or 7/6. Now again, those problems that we did there in the sheet are pretty straightforward. You'll see some more interesting things in your assignment in the homework. You might have to use some ideas from previous units, like walk around maybe, 30, 60, 90, stuff like that. You can't forget all those things that we've done before. So remember, do the best you can, the homework, get that submitted. And then remember, after you submit it, if you had questions on something that you want to get addressed, you can always resubmit later on up to a week. And just make sure if you do resubmit that you resubmit everything so I can see the entire assignment. So I grade grade out of 2 points first, and then I'll fully grade it about a week after the due date. Okay? All right, take care. I'll see you later. Bye-bye.